Have you ever imagined what lurks in the darkest corners of our universe? Are you ready to confront the cosmos' most terrifying and inexplicable secrets? Dear traveler, welcome. Today we're off to explore the deepest mysteries of the universe. From black holes that devour everything in their path, to dying stars that explode in devastating supernovas, to strange planets with hellish conditions and unexplained cosmic signals that reach us from the farthest reaches of space. Prepare to plunge into a world where the laws of physics are pushed to their limits, where reality surpasses fiction, and where each discovery raises as many questions as it answers. But before you set off on a new adventure, remember to like the video and subscribe to the channel so you don't miss a thing. Thank you, and have a great trip! The universe was born 13.8 billion years ago. The Big Bang. We often speak of the observable universe, but we know that it doesn't stop at the limits of our observation. There are planets, stars, black holes, asteroids, comets, and many other celestial objects. All these bodies form galaxies, then clusters and even superclusters. We study what's happening beyond our solar system, beyond Neptune. We find other planets, exoplanets. New stellar bodies are discovered. Some are easily identified and explained. Others are still mysterious. If you ask the people around you what they find mysterious about the universe, many will say black holes. How do we know they exist when we can't see them? Astronomers know they exist because of the effect they have on objects that come too close to them. Black holes swallow up everything, even light. That's why we can't see them. We know that they appear when a giant star runs out of energy. It implodes and its center collapses under its own weight, triggering an explosion called a supernova. The star is then reduced to a very compact ball, characterized by a very large mass in a very small space. This is the singularity. The gravity of a black hole is so strong that it attracts everything that passes near it. The black hole can even swallow stars. Nothing is fast enough to escape it, not even light. The zone around the black hole, into which bodies are drawn, is called the ergosphere. There are 3 types of black hole. Stellar black holes are the most common, with a mass at least 3 times that of the Sun. Supermassive black holes, whose mass is at least 1,000,000 times greater than that of the Sun. They are found at the center of galaxies, and their presence sometimes causes the appearance of jets and X-rays. We don't really know how they form. Sagittarius A, at the center of our Milky Way galaxy, is a supermassive black hole weighing 4,000,000 times the mass of the Sun. Others are even more enormous. Intermediate black holes, as their name suggests, fall between the 2 previous categories. Their mass ranges from 100 to 10,000 solar masses. They were only discovered in the 2000s. At this stage of our journey, let's make a short stopover to quasars. A quasar stands for quasi-stellar radio source. The first to be discovered was 3C273, At first, astronomers thought it was a new star, but thanks to a radio telescope, they discovered that it produced 1,000,000 times more radio waves than a normal star. They realized that this was a very distant galaxy, located 2.44 billion light-years from Earth. Normally, at this distance, it would have been very faint, but this object was the brightest in the universe observed at the time. Astronomers first thought that it was a measurement error before discovering other similar spectra. They even discovered quasars that emit gamma rays, the highest energy carried by light. Today, there are over 1 million of them. Although they are the brightest stars in the universe, they cannot be observed with the naked eye. They are all located between 10 and 11 billion light-years from Earth. They were formed when the universe was young, between 2 and 3 billion years old. In short, quasars are at the heart of very distant, very luminous galaxies with very active cores. They are surrounded by an accretion disk that is very rich in matter and therefore very dense. Matter that heats up and glows before being swallowed up by the black hole. Quasars are thought to play a part in the formation of galaxies. They disappear naturally as the energy in the accretion disk diminishes. Researchers have also discovered blazars and radio galaxies in the same location, but they are thought to be the same phenomena, observed from a different angle. There are still many unanswered questions. Do all galaxies pass through the quasar stage? If so, at what point in their evolution? But the black hole is not only an ogre of space, it can also distort time. Ever since Albert Einstein, we've known that gravity distorts space-time. The curvature of space-time produced by an object is proportional to its mass. Imagine a marble placed on a taut cloth. It rolls towards the middle, and the cloth sinks under its weight. The greater its mass, the deeper the fabric sinks. If you place other, lighter objects on the fabric, they will slide towards the marble. The most massive marble in existence would represent the black hole. The objects attracted by the hole form an accretion disk around it, and we can see it. As the matter swirls, it heats up and produces light. But let's get back to the subject of time. An astronomer visiting a black hole would see no difference on his watch. He'd feel as if he'd gone for an hour, whereas in reality, years would have passed for his colleagues who remained in the rocket. But he wouldn't come back from such a trip. He'd be pulled inside and stretched out like spaghetti. What does a black hole look like? Black holes are represented as a giant funnel into which everything is absorbed, but never emerges again. The limit that cannot be crossed is called the event horizon. Beyond this limit, there is no chance of escape. The size of this horizon varies according to the mass of the black hole. For 10 solar masses, it is 60 kilometers or 38 miles. The accretion disk revolves around this horizon before being swallowed up forever. The temperature of the event horizon is very high, whereas inside the black hole it's very cold. Since black holes exist, do white holes also exist? The answer is still theoretical. A white hole, also known as a white fountain, would be the opposite of a black hole. It would simply expel matter and light. Just as it is impossible to escape from a black hole, it would be impossible to enter a white hole. Some scientists are beginning to talk about their existence outside the realm of mathematics. They have devised a convincing scenario to explain their formation. They are the ultimate stage in the evolution of black holes. Matter that has entered a black hole will come out again as it transforms into a white hole. What happens to black holes? They evaporate over time. This happens in the form of radiation, known as Hawking radiation, named after the famous astrophysicist and black hole specialist. Because of this radiation, black holes have a limited lifespan. In practice, Hawking radiation is extremely weak for stellar or supermassive black holes. Its detection is still impossible today, mainly because black holes are so cold. The existence of Hawking radiation poses a problem known as the information paradox, which still divides scientists. The paradox lies in this: any object sucked into a black hole disappears forever, as I told you above. But quantum mechanics tells us that everything is information, and that information never disappears. Stephen Hawking proposes the hypothesis that information remains at the edge of black holes in the event horizon. Eventually, it would be spat out by Hawking's radiation. On April 10, 2019, the first images of a black hole are published, that of M87, a supermassive black hole located at the heart of the M87 galaxy. These were followed on May 12, 2022, by images from Sagittarius A at the center of the Milky Way galaxy. Capturing a clear image of Sagittarius A is a monumental challenge. Unlike M87, where the brightness of the gas disk remains stable for several hours, Sagittarius A shows extremely rapid variations in brightness, of the order of 20 seconds. The variability considerably complicates the capture of clear images, requiring the integration of numerous photos to obtain an average image. This integration process can result in a loss of precision and a less sharp image. Reconstructing images of black holes from interferometric data is a complex process. With limited resolution and a small number of radio telescopes, images have to be mathematically reconstructed, which can introduce artifacts. For example, the 3 bright spots observed in the luminous ring of Sagittarius A are probably reconstruction artifacts, rather than actual features of the hot gas surrounding the black hole. But the most intriguing aspect of these images of the black hole is that the center is not completely black. If the black hole were to absorb all light, its center would have to be completely dark, which is not the case in the images of M87 and Sagittarius A. If the explanations linked to the reconstruction of the images turn out not to be valid, this could call into question our understanding of how black holes work. But in any case, it's unlikely that Earth will encounter one. We're far more likely to encounter a star because there are so many more of them in the universe. By the way, let's take a look at some mysterious stars. Neutron stars are the remnants of massive stars that have reached the end of their lives. Their existence has only been known since the late 1960s. Only ordinary stars with masses between 8 and 40 times that of the Sun become neutron stars. A neutron is an elementary electrically neutral particle making up the atomic nucleus. When supernovae explode, the outer layers of the star are thrown off into space, but the central core remains. There is no nuclear fusion to counterbalance the pull of gravity, so the star condenses and collapses in on itself. What's left is a bare core, very dense and compact, composed mainly of neutrons. Neutron stars are the densest stars in the universe. To give you an idea, 1 teaspoon of the material that makes them up would weigh as much as Mount Everest, or 4 billion tons. To describe it, imagine a sphere made up of several layers. First, an outer layer of ions and free electrons. Next, an inner crust up to 2 kilometers or 1 mile thick, made up of free neutrons, neutron-rich nuclei, and electrons. Then comes an outer core made up of neutrons, protons, and electrons. And finally, an inner core, whose density is so great that we don't know exactly what it's made of, perhaps a reorganization of the inner constituents of neutrons and protons, called quarks. As you can see, a neutron star is a kind of giant atomic nucleus, composed essentially of neutrons and possessing an extraordinary density. These stars rotate several hundred times per second. It's enough to make you dizzy. There are 3 types of neutron stars. The first are pulsars. These are neutron stars that turn on themselves very quickly, reaching speeds of 252 million kilometers per hour, or 157 million miles per hour. From Earth, they appear to blink, hence the name pulsar. Pulsars rotate for several million years before emptying out and becoming normal neutron stars. The second are magnetars. They are much rarer and possess the most powerful magnetic fields in the universe. In 2004, a magnetar succeeded in modifying the upper atmospheric layers of our Earth. And finally, millisecond pulsars. These are very old pulsars. In 2019, the most massive neutron star was 25 kilometers or 15 miles in diameter. Not so big, is it? In late 2022, astronomers observed a neutron star that challenged them. It was overweight. No, stars don't have to keep their figure like models, but they do obey physical criteria. And our scientists couldn't understand how a neutron star could be so fat. It defied all theories. This star was born from the fusion of 2 smaller neutron stars. Normally, it would have collapsed into a black hole. The star remained visible for more than a day. Its lifespan remains a mystery. Some researchers believe it was spinning so fast with such immense magnetic fields that its collapse was delayed. They now hope to catch a glimpse of other stars so they can be better observed. Scientists would like to understand why the heaviest stars become black holes and at what threshold they turn into neutron stars. They'd also like to know what lies at the center of these stars. What might the compressed matter look like? In the universe, there are red and blue giant stars. Contrary to the symbols on your map, red stars are cold while blue stars are hot. But what is a supergiant? Stars with masses of between 10 and 40 solar masses are blue giants. They have a very short life expectancy, from 10 to 100 million years. When they have consumed all the hydrogen in their core, they fuse helium, their outer layers swell, and their temperature drops. At the end of their lives, they transform into red giants. They produce increasingly heavy elements, such as iron, nickel, chromium, cobalt, and titanium. Their core collapses, and they evolve either into a black hole, or in the case of the smaller stars, into a neutron star. Their luminosity is far more intense than that of the Sun. Stars are classified visually on a map, the Hertzsprung-Russell diagram. It shows that most stars follow a line. Far below this line are the white dwarfs, and above them are the giants and supergiants. What scientists would like to understand is their strange behavior. Some of them go backwards. Some red giants, thought to be at the end of their lives, have reverted to blue giants and exploded at that point. Others change their minds again, eventually reverting to red before exploding. Sometimes they even explode at the intermediate stage, that of yellow giants. As you can see, they don't always follow a set pattern, and that's what puzzles researchers. Let's take an example. Perhaps you've heard of Betelgeuse? It's the second closest red supergiant to the solar system, long known and easy to observe. It lies in the constellation Orion. Its diameter is around 750 times that of the Sun. Researchers study it because it tells us a lot about giant stars. It too sometimes behaves strangely. In January 2020, its luminosity abruptly diminished and it began to rotate much faster than usual. Some thought it would soon explode, but it didn't. Scientists put forward the following explanation. It expelled a spherical cloud of dust that partially concealed it. Nor would it have changed its speed of rotation. Its bubbling surface would have been mistaken for rapid rotation. In the end, its luminosity did not diminish, but its diameter did. In 15 years, it would have lost the distance from Venus to the Sun, and this process seems to be accelerating. Researchers are currently speculating on processes that are modifying the convection of giant cells and affecting measurements. Convection is the set of internal movements, both horizontal and vertical, generated in a fluid mass. All these changes, close together in time, would indicate an imminent end. Scientists don't agree on this either. Some think Betelgeuse is in the final stages of carbon fusion, while others believe it is in the helium fusion stage. Some even claim that it has already exploded and that information from this event is on its way to Earth. We observe phenomena, draw conclusions, and then discover an exception that calls everything into question. To help us see things more clearly, scientists are banking on the study of gravitational waves. In the 17th century, Newton theorized universal gravitation. Masses attract each other, with variations depending on their weight and distance. In the 20th century, Einstein proposed a different vision. The mass of objects distorts space-time. Remember the marble placed in the middle of a taut cloth? It would attract any other object placed on the cloth. According to Einstein, it's not the marble that attracts the other marble, but the deformation of space created by its mass. So, the greater the mass of an object, the greater the curvature of space-time, the greater the gravity. A very massive object, such as a giant star, moving through space-time, will displace this curvature and create a disturbance in the latter. This is the gravitational wave. The perception of these waves opens a new window on the universe. In 1974, the discovery of the first binary pulsar provided indirect evidence of the existence of these waves. It was then necessary to build instruments capable of detecting them directly. The LIGO project in the USA and the Virgo project in Europe were born. It took some time before they could be detected, as they require objects of staggering mass and are of very low frequency. In 2015, gravitational waves were detected from two colliding black holes. These black holes were 36 and 29 solar masses respectively. We now believe that these two black holes have been spinning towards each other for billions of years. As they got closer, their orbits accelerated until they swirled around each other at breakneck speed, emitting colossal amounts of energy in the form of gravitational waves. The black holes emitted more energy than the entire universe, in all forms of radiation, and then merged. The new black hole thus created oscillated for a few moments before stabilizing. This collision is known to have occurred around 1.3 billion light-years from the Milky Way. In 2016, researchers observed their first neutron-star merger and succeeded in explaining many previously mysterious phenomena. But how can gravitational waves be observed more precisely? Earlier, we explored pulsars. These are very useful for detecting gravitational waves. They send out very regular radio signals, sometimes several hundred times a second. Researchers have used a network of over 100 pulsars, hoping to detect minute variations in the frequency of the signals they emit. Using a system of mirrors placed a few thousand kilometers apart, the scientists spotted a more stretched signal, equivalent to changes of less than a millionth of a second over more than 20 years. Incredible, isn't it? Yet it's enough to prove the existence of a gravitational wave. These oscillations in the curvature of space-time are produced by very violent phenomena, such as the explosion of a star, the collision of two neutron stars, or the merging of black holes. Gravitational waves seem to pass through the Earth at every instant, but fortunately we don't perceive them. Like electromagnetic waves, gravitational waves carry energy, momentum, and angular momentum. Scientists believe that gravitational waves resulting from the Big Bang may have left observable traces in fossil radiation. They would like to find these traces, as their discovery would provide a better understanding of the beginnings of the universe and its evolution. Gravitational astronomy, as it's known, is therefore very young, but very promising. The number of detections continues to grow, and we are now seeing the beginnings of statistically relevant trends. Scientists hope to use these statistics to refine the measurements of Hubble's constant. Gravitational waves are already revolutionizing our knowledge of stellar evolution, galactic astrophysics, the physics of dense stars and extreme matter, and primordial cosmology, projects are underway to create giant detectors and diversify detection techniques. Now we can listen to the universe. But enough about stars. They're not the only ones shrouded in mystery. Some planets also intrigue researchers. We're fairly familiar with the 8 planets in our solar system, but what about the more distant planets? Those that lie beyond our solar system? We call them exoplanets. They are difficult to observe, not only because of the distance separating them from us, but also because they often revolve close to their very bright star. The Hubble Space Telescope and the Paranal Observatory in Chile provide us with interesting observations. This observatory is currently one of the world's leading centers for the study of exoplanets, thanks to the Sphere Adaptive Optics instrument. This instrument produces images of young massive exoplanets and protoplanetary disks surrounding stars, suspected to be the regions where they form. The first images of an exoplanet were taken in 2005. M1207b is a planet more than 5 times the mass of Jupiter. It orbits at twice Neptune's distance from the Sun. It is so far from its host star that it took almost a year to demonstrate that it was gravitationally bound to that star. The observatory also studied a closer planet, Beta Pictoris b, in 2003. Its discovery was not announced until 2008. It lies 8 times the Earth-to-Sun distance from its host star. It is a very young, very hot, and very luminous planet, with a mass 13 times that of Jupiter. Estimated to be less than 20 million years old, it is so young that the accretion disk around its host star is still visible. Highly sophisticated instruments are needed to observe these planets. You also need to distinguish between the light reflected by the planet and that emitted by its star. Before an exoplanet can be imaged, it must first be detected. Michael Mayer and his student discovered the first exoplanet in 1995. They detected oscillations in the spectrum of the star Peg 51, which would correspond to a planet. They spent the summer verifying their information before announcing the news. 51 Pegasi b is a new planet, very different from those we know. It orbits its star in just 4 days and is so close to it that its temperature exceeds 1,000 degrees Celsius, or 1,832 degrees Fahrenheit. This will revolutionize the search for planets outside the solar system. Now we know where to look, and we're finding them. Today, we've located over 5,500 planets, including several multiple planetary systems. Between 2009 and 2018, the Kepler mission discovered over 2,600 planets. The diversity of these planets is much greater than in the solar system. Observation methods have evolved, and we now use the transit method. This method consists of observing a star continuously and measuring the drop in luminosity as the planet passes in front of it. This eclipse makes it possible to deduce the planet's radius and provides an additional constraint on the inclination plane of the planetary orbit. The discovery of exoplanets calls into question many certainties about the workings of the universe. Our knowledge is based on the study of our solar system, with its 8 planets in precise positions, whose movements are predictable over the long term. The quasi-random distribution of giant planets in exoplanetary systems came as a surprise and highlighted the fact that there were other systems operating differently. We discovered that a planetary system can be chaotic, dynamic, and sometimes unstable. But what do we know today about exoplanets? Most exoplanets are very different from those in our solar system. Because they are close to their star, they are very hot. We call them hot Jupiters. They have a thick atmosphere, mainly made up of hydrogen and helium. The clouds found on these planets are composed of materials more surprising than water, such as titanium or carbon. We often talk about their large size, but some of them are small, a little bigger than the Earth. But what interests us most is whether they can harbor life. Yes, the same old question. We know that some exoplanets are located in the habitable zone, i.e. at a distance from their star, where the temperature would allow the presence of liquid water on their surface. Of the 5,500 exoplanets on record, only around 50 are Earth-sized and lie within this habitable zone. But for the moment, we don't know what they're made of. To do so, we need to know their diameter and mass in order to deduce their density. From these parameters, scientists can determine whether they are rocky or gaseous. Researchers have identified a number of planets that could meet the conditions required for the development of life. The Hubble telescope has detected water in the atmosphere of one exoplanet, but the planet's temperature of 425 degrees Celsius, or 797 degrees Fahrenheit, makes it uninhabitable. All that remains now is to continue the search and take a closer look at these curious planets. Researchers have also observed some strange planets. The planet WASP 103b, 1.5 times larger than Jupiter, is shaped like a rugby ball. This shape is thought to be due to the intense tidal forces of its star. XO3b, observed by the Spitzer telescope, is 11 times more massive than Jupiter and completes its orbit around its star in just 3 days. It goes from winter to summer in just a few minutes. In WASP 121b's atmosphere, a metallic vapor would see aluminum condense with oxygen to form corundum. This compound would produce rubies and sapphires if combined with other metals, precisely those present in this planet's atmosphere. As you can see, exoplanet research is still in its infancy, and it's an exciting one at that. A real treasure hunt for our scientists. Let's return for a moment to protoplanetary disks. We've seen them briefly before, but do you know what they are? It's a disk that revolves around a young star in formation, made up of gas and dust from which bodies form. Its radius is of the order of a few hundred astronomical units. It's quite thin but not flat, and warmer at the center than towards the outside. By studying them, we can better understand the genesis of planets. Scientists had theorized about the existence of these disks and their role in the creation of planets. They suspected they existed, but it wasn't until 1995 that the Hubble Space Telescope photographed several of these disks. A protoplanetary disk is made up of around 99% hydrogen and helium and 1% heavier elements. So a lot of gas and very little dust. These include oxygen, carbon, silicon, iron, and nickel in solid or vapor form. Planets form in these disks in several stages. The dust elements stick together, then grow rapidly under the influence of gravity. The planet then undergoes oligarchic growth, which is calmer but still impressive. In 2023, the James Webb Telescope made a fascinating discovery by observing the composition of a protoplanetary disk. In other words, the ingredients of a future planet. Among these ingredients, there's a lot of carbon. This disk was chosen because its star, J160532, is rather young, so planets are not yet formed. Carbon atoms have combined with hydrogen atoms to form some of the most astonishing molecules ever found in a disk. Scientists believe that the carbon was in the form of grains that were vaporized by the star's intense activity. That's why it's so present in this disk. This scenario is very similar to the one that led to the formation of the Earth. Understanding it would help us to better understand the formation of the solar system and the planets that make it up. It now remains to be seen whether this discovery is an exception, or whether all disks around small stars have this overabundance of carbon. We know that gas giant planets are not the only bodies to have a ring. Some small celestial bodies crisscrossing the solar system beyond Neptune also have a ring, such as Chariklo or Haumea, whose ring was discovered in 2017. All these rings lie within a certain distance of the central body, known as the Roche limit. But now the European Cheops satellite, pointing towards Quasar, an icy dwarf planet, has discovered that it too has a ring, where there shouldn't be one. The ring would be 4,100 kilometers or 2,600 miles outside the Roche limit, twice as far as previously thought to be the maximum distance. It should normally disperse. The ring material should accrete and form natural satellites. Quasars' freezing temperatures could play a role, preventing ice particles from sticking together, but further research is needed to fully understand this phenomenon. The study of these dwarf planets, Quasar is half the size of Pluto, is made difficult by their small size and remoteness. This discovery challenges theories about how ring systems are formed. But what is a dwarf planet? The term dwarf planet was defined in 2006. A dwarf planet orbits the Sun and has sufficient mass to be in equilibrium, surrounded by smaller solid or gaseous objects. The fact that its orbit is not cleared of these objects distinguishes it from other planets. But in reality, a dwarf planet is not considered a planet. It lies somewhere between a planet and an asteroid. In our solar system, the criteria are a diameter of between 1,000 and 2,500 kilometers, or between 620 and 1,500 miles. To give you an idea, Mercury's diameter measures 4,880 kilometers, or 3,000 miles, although Mercury is the smallest of the planets. Next, a dwarf planet has a spherical or ovoid shape, whereas asteroids have irregular shapes. It must orbit the Sun, which excludes satellites of other planets. Finally, it must not have cleared its orbital neighborhood. Today, 5 stars are considered dwarf planets. In descending order they are Eris, Pluto, Ceres, Makemake, and Haumea. They're all smaller than the Moon. Let's move on to one of the most beautiful things in the universe, nebulae. The name alone evokes mystery. The adjective nebulous evokes something that lacks clarity, that is hidden by clouds, that is blurred and therefore mysterious. It also evokes a bad omen. Let's hope that's not the case in astronomy. Let's take a closer look. For a long time in astronomy, the term nebula was used to describe any celestial object with a diffuse appearance. Today, the prevailing definition is that of a celestial object composed of rarefied gas, plasma, or interstellar dust. By dust, as you already know, we mean tiny rocky grains containing silicate, aluminum oxide, and calcium. The dust doesn't emit light, but it diffuses it very well and in all directions. Nebulae are among the most beautiful celestial objects. What do they look like? They are difficult to observe with the naked eye, but the Hubble and James Webb telescopes have provided us with many images. We see colored clouds of blue, violet, and pink, a bit like a spot of gasoline on the ground. The colors are spread out against the black background of space, and points of light are added to the giant stain. Astronomers are understandably fascinated by their beauty. Are there different types of nebula? Yes, there are 6 main groups. Firstly, planetary nebulae, named by William Herschel in 1785. Through his telescope, he saw a circle resembling a planet. In fact, they were gigantic bubbles of gas ejected from around a dying star. The most impressive of these were the Helix and Lyra stars. A photograph of the latter shows a blue circle surrounded by an orange halo. Secondly, there are reflection nebulae, which consist of immense clouds of dust and hydrogen, reflecting the light of one or more nearby stars. They are usually blue. Supernova remnants are very large nebulae. They form following the implosion of a dying supermassive star, or the explosion of a white dwarf. These nebulae have a fairly limited lifespan, on an astronomical scale, of course. The Crab Nebula and the Swan's Laces are 2 such nebulae. They resemble long blue and yellow threads, with lighter or darker reflections crossing the sky. The Crab Nebula lies 6,300 light-years from Earth. Its beautiful blue color and impressive pulsar spinning on itself 30 times per second make it one of the most fascinating objects in the sky to observe. Nebulae located around certain Wolf-Rayet stars are known as Wolf-Rayet bubbles. They are located around very massive, very hot stars, reaching the end of their life. They form as a result of the progressive expulsion of the outer layers of these stars. Examples include Thor's Helmet Nebula and the Crescent Nebula. The image shows a large blue and pink cloud studded with white, blue, and orange points of light. Ionized hydrogen regions, or HIIs, form another type of nebula. This type takes the form of hydrogen clouds with several ionized atoms. An ionized atom is a neutral atom that has lost or acquired electrons and thus become an electric charge carrier. These nebulae are often associated with open clusters of young stars, whose proximity leads to the ionization of the hydrogen they contain. Tarantula is one such region, but fortunately, it doesn't look like a big hairy spider. It looks more like a mass of red and orange clouds, with a white zone at its center. But perhaps those who named it have perceived the silhouette of a spider. The most famous region of ionized hydrogen is Orion. It lies 1,350 light-years from Earth in the Milky Way. You can easily observe it with the naked eye, in the absence of light pollution, if you're in the northern hemisphere. It's located in Orion's sword, an alignment of 3 stars. It is entirely illuminated by a group of 4 very massive, very luminous stars at its center, called the trapezium. The Pillars of Creation, first photographed in 1995 by the Hubble telescope, are also part of the HII. They resemble the Earth-colored concretions found in caves, but are columns of gas. Dark nebulae are the 6th type of nebula. They are made up of thick clouds of interstellar dust and noble gases, which absorb part of the light that passes through them. As a result, they are very dark, even obscuring other nebulae or stars. The most spectacular of these are the Horsehead and the Coal Sack, which form the darkest part of the Milky Way. Personally, I don't see a horse's head, but rather a dark headless man looming over a pink background. But maybe it depends on the photo you're looking at. There are thousands of nebulae in the universe, some more impressive or beautiful than others. The only ones observable with the naked eye are Orion and the Carina. The others are too far away from us, so you'll need powerful astronomical binoculars or a telescope to catch a glimpse. You'll also need to be far away from any light sources, which is becoming increasingly difficult. Nebulae are where stars are born or die. Give birth to a star? Isn't that magical? You also understand that the shapes and colors of nebulae depend on their density and the materials and gases that make them up, as well as on temperature. Hydrogen, for example, glows pink, while oxygen glows blue. The density of a nebula is very low, just a few thousand atoms per cubic centimeter. In comparison, the Earth's atmosphere is 1,000 times 1,000 billion times denser. Simply put, a nebula is a pretty empty cloud. Speaking of clouds, have you ever heard of the Oort Cloud? The Oort Cloud is said to be a sphere of frozen comets, inactive and invisible, which surrounds the solar system at great distances. It would be located at the edge of the solar system, well beyond the orbit of the planets. Its outer limit, forming the gravitational boundary of the solar system, would be more than 1,000 times the distance between the Sun and Neptune. It is named after the Dutch astronomer who published the results of his work on comets in 1950. No direct observations have been made, so it's still theoretical. But scientists have used their analysis of comet orbits as a basis for imagining its existence and shape. Researchers now claim that comets originate in 2 very distinct places: the Kuiper Belt, to which I'll take you in a moment, and the Oort Cloud. According to some, The latter extends up to 30,000 billion kilometers. It would take a spaceship around 300 years to reach its inner limit, enough to discourage anyone with the idea. It contains the bulk of the solar system's comets and even feeds the Kuiper Belt. It is said to be made up of 1,000 billion comets, with a mass equivalent to 40 Earth masses. But don't get the idea that this is a very dense cloud. The rock and ice cores that make up the cloud are separated from each other by around 10 million kilometers or 6 million miles. This cloud is absolutely gigantic. It's probably made up of celestial objects ejected during the genesis of the solar system through phenomena such as resonance with giant planets. These objects are composed of icy water, ammonia or methane. This giant cloud is made up of two parts: an inner disk, known as the inner Oort Cloud or Hills Cloud, shaped like a torus, and an outer spherical assembly, known as the outer Oort Cloud. Quite simply, the outer cloud is thought to be the source of most long-period comets. The inner cloud would be the source of Halley-type comets. Short-period comets come from the Kuiper Belt. Let's take a closer look. The Kuiper Belt is a region located in the plane of the solar system beyond the orbit of Neptune. It forms a ring around the solar system, hence the name Belt. It owes its name to the Dutch astronomer who suggested its existence in 1951. It probably begins between 30 and 55 astronomical units and extends to 100 to 150 astronomical units. As a reminder, an astronomical unit is the unit of measurement corresponding to the average distance separating the Earth from the Sun, i.e., 150 million kilometers. But despite its size, the total mass of the objects in the Kuiper Belt is only 10% of the Earth's mass. It is thought to contain over 200 million small icy bodies, small asteroids and bodies likely to become comets. These bodies were unable to come together to form a planet due to the presence of Neptune in its vicinity. Neptune's immense gravity prevented the small bodies from merging. The Kuiper Belt also contains a few fairly large bodies, such as the 4 dwarf planets. Pluto, whose diameter measures around 2,375 kilometers or 1,500 miles. Together with its moon Charon, they form what is known as a binary. Eris, 2,326 kilometers or 1,500 miles in diameter, but denser and more massive than Pluto. Makemake, 1,430 kilometers or 900 miles in diameter. Haumea, 1,632 kilometers or 1,000 miles in diameter, which is egg-shaped and has a ring. Another object, Ixion, was discovered in 2001. Its nature is not well known, and it has not yet been classified as a dwarf planet, or rather as an asteroid. Here again, giant planets play a role. It's the gravitational perturbations they generate that occasionally alter the orbit of one of these bodies, triggering a change in trajectory towards the Sun. The Kuiper Belt was only a hypothesis until 1992, when images of the sky finally revealed bodies more than 30 astronomical units away. They are difficult to see, not only because they are so far away from us, but also because their apparent motion is so slow. They take several centuries to complete one orbit around the Sun. From Earth, only the largest objects are observable, those generally over 100 kilometers or 60 miles in diameter. This belt is of interest to researchers for at least two reasons. Firstly, it is likely that the objects in it are extremely primitive remnants of the solar system's early accretion phases. It is also thought to be the source of short-period comets. A recent theory asserts that it didn't form where it is today, it formed closer to the Sun. It would be Neptune, moving away from the Sun, that would have pushed it to its current position. The study of Kuiper Belt bodies and their movements has led to an exciting new study: the search for Planet 9. This mysterious planet is thought to be the size of Neptune. Some astronomers believe it exists, and that it is the reason why certain bodies in our belt have a particular orbit. It could be linked to the gravitational influence of a planet. Research is ongoing, but no space mission is planned for the moment. The only probe that has closely studied the Kuiper Belt is New Horizon, which flew past Pluto in 2015 after a 9-year voyage and explored Arrokoth in 2019. Arrokoth has become the most distant body in the solar system explored by a spacecraft. I've told you about long-duration and short-duration comets, but what exactly is a comet? A comet is a more or less spherical body up to 10 kilometers in diameter. It is made up of ice and dust. Its name, meaning tail, comes from the Greek coma. As it approaches the Sun, some of its matter sublimates, meaning that the icy water becomes gaseous. The star then develops a trail of gas several million kilometers long. This material reflects the Sun's light, making it visible from Earth. Comets have been spotted since antiquity, appearing in paintings and engravings. Nearly 4,000 comets have been discovered to date. They formed with the solar system in its cold regions 4.6 billion years ago. As we've just seen, they form in two places: the Oort Cloud and the Kuiper Belt. There are two types of comet. Short-period comets, known as periodic comets, originate from the Kuiper Belt. Their period is less than 200 years. They pass close to the Sun on a regular basis, but lose part of their mass during each passage and eventually die out for lack of material to sublimate. Long-period comets, more than 200 years old, originating from the Oort Cloud. They pass close to the Sun only once, and are said to be non-periodic. The life expectancy of periodic comets is very short. So how can there still be any after 4.6 billion years? Simply because long-lived comets sometimes become short-lived comets when they pass close to a planet. Their trajectory can then be altered, resulting in an elliptical orbit. Comets have cyclical periods of activity as they follow an orbit. They take years to complete their orbital revolution. Thanks to astronomers' calculations, we can see them from time to time. We know when they will pass. One of the most famous comets is Halley's Comet, which has a cycle of 76 years. This cycle was first spotted in 1705 by the Englishman Edmund Halley. The comet's irregularly shaped nucleus is 16 kilometers long and 8 kilometers wide. Its tail may extend for some 50 million kilometers or 30 million miles. Its surface features hills, valleys, and craters, from which escape gas and dust that feed the comet's hair and tail. Last seen in 1986, it will be visible again in 2061. It reached its aphelion, the furthest point of its orbit from the Sun, in December 2023. It has therefore begun its return journey in our direction. Halley is also the first comet to have been approached by probes. The Soviet space probes Vega 1 and 2 crossed its nucleus at less than 9,000 kilometers, or 6,000 miles. Then the European probe Giotto, which approached to less than 600 kilometers, or 370 miles. Now, in April 2024, you may have caught a glimpse of another comet, the Mother of Dragons, also known as the Devil's Comet. The best day to see it was April 21st, as it will reach its perihelion, its closest point to the Sun. She's back after a 71-year journey. All you need is a pair of binoculars or a small telescope. Its nickname comes from the fact that it periodically expels the contents of its icy core into space, enhancing its brilliance. Its composition of ice, dust, and rock gives it an emerald-colored head due to the presence of diatomic carbon molecules in sunlight. A flare in 2023 caused horns to appear on its surface, so it's also known as the Devil's Comet. It is one of the 10 largest comets known to date. In 1811, an amateur astronomer spotted comet C1811F1, which was visible for 9 months. But comet Hale-Bopp holds the record for the longest period of visibility, with 18 months between 1996 and 1997. Before continuing our journey, you should know that the shooting star showers we regularly witness are caused by the Earth crossing a rocky body. So you've understood that shooting stars aren't actually stars. They're also known as meteors. These luminous phenomena occur when dust particles from a comet or asteroid collide with the Earth's atmosphere. These dust particles enter the atmosphere at very high speeds, up to 70 kilometers per second, or 40 miles per second. They ignite as they rub against the air, causing them to ionize and incandesce. Mother of Dragons I've just told you about is the source of an annual shooting star shower, the Kappa Draconids, which can be seen from mid-November to mid-December. Since we've mentioned asteroids, let me explain what they are. Asteroids are also debris from the formation of the solar system, but they lie mainly between Mars and Jupiter in the main belt. Their composition differs from that of comets. In simple terms, they are dead, ice-free bodies. They are classified into 3 families: carbonates, which are the most numerous, silicates, and metallic. Astronomers have identified more than 1 million asteroids over 1 kilometer in diameter. Some asteroids leave their usual geographic zone. They are known as near-Earth asteroids. They are deviated from their normal trajectory and may cross the orbit of planets like Earth. Every year, 27,500 asteroids pass close to the Earth. NASA keeps a close eye on them. Scientists study them with great interest, always with the aim of understanding the birth of the solar system. But meteorites also pass close to the Earth. So what's the difference between a meteorite and an asteroid? A meteorite is much smaller than an asteroid or comet. What's more, some have managed to land on Earth. It is estimated that 90 meteorites have landed in France over the last 500 years. A meteorite looks like a black calcined rock with a smooth surface and sharp angles. It is also heavier than a conventional stone. We're already nearing the end of our journey. We have encountered several celestial objects, some made of hard material, others more gaseous. Researchers are also intrigued by another phenomenon, ultra-high energy cosmic rays. A cosmic ray is a fast-moving charged particle from the interstellar medium. These particles are mainly protons, 85%, helium nuclei, 14%, electrons and other atomic nuclei originating from the cosmos, space, and even the sun. Their energy is typically 1 GeV, the energy of an electron accelerated by 1 billion volts of electricity. The Earth is constantly bombarded by radiation from the cosmos, but some exceptional rays deserve our attention. The energy of some rays can reach up to 10 to the 11th power GeV. This may not sound familiar, but it's absolutely enormous. These rays represent a real enigma for astronomers. These very high-energy rays are very rare, with only a few events per square kilometer per century, and only a few dozen observations worldwide in 60 years. In theory, such rays, presumed to be protons, should be slowed down in their course by the gas of very diffuse photons that form the famous cosmic rays. How complicated is that? In short, they shouldn't reach our atmosphere. And yet, here they are. Let's take an example. In 2021, a very high-energy cosmic ray was detected at a level rarely reached. It happened in the Utah desert. This ray, called a Matarasu, was the second most energetic cosmic ray ever recorded since Oh My God in 1991. The Array telescope in the USA detects these rays, as does an observatory in Argentina. Researchers at these two observatories disagree on the exact measurement of their energy. Amaterasu's composition and origin remain a mystery. The charged particles are deflected by our galaxy's magnetic field, so there is some doubt as to their direction of arrival. Some believe that matter accreted by massive black holes at the center of galaxies could form jets of matter at very high speeds, producing cosmic rays. We still have a lot to discover about these mysterious rays. To do this, researchers need to build new, even more sophisticated instruments. An exciting challenge for the scientific community. In the meantime, rest assured that these rays are not dangerous for us, as long as we remain on Earth. The Earth's atmosphere and magnetic field protect us from most of the rays coming from space. Before we end our journey, let's take a look at some recently discovered phenomena. The European Space Agency's Cheops Space Telescope has detected a rainbow-like phenomenon on the exoplanet WASP 76b, 640 light-years away. This is the first time such a phenomenon has been observed outside our solar system. This shimmering sphere of light is called glory. It is caused by light from the host star, reflected by clouds of iron that drip down in a shower of iron. This recent discovery has yet to be confirmed. In June 2021, British astronomers discovered a giant arc stretching across around 7% of the observable universe. Earlier this year, the same researchers spotted a second giant structure, the Big Ring in the Sky. Both structures are located in the same cosmological neighborhood and remain inexplicable. Such phenomena are incompatible with the existing cosmological model. They exceed the size limit considered viable, according to our usual models. This limit lies at 1.2 billion light-years, while the giant arc extends over nearly 3.3 billion light-years. The Great Ring extends over 1 billion light-years. Its apparent size from Earth is equivalent to 15 times that of the Moon. Scientists wonder about the forces and conditions that could have led to such a structure. After all, our ring isn't really a ring at all. It's more like a spiral, which is quite rare. These two discoveries present researchers with a double challenge. They may be forced to reconsider current cosmological models, particularly those concerning the formation and evolution of large-scale structures in the universe. The large ring could be the result of processes that are still unknown or poorly understood. In 2017, astronomers discovered another mysterious object resembling a pebble 150 meters long and 100 meters wide. Nicknamed Oumuamua in Hawaiian, meaning messenger, it has been the source of much debate. As the first interstellar object to cross our solar system, no one could agree on its true nature: asteroid, comet, or even fragment of an exoplanet. Unlike most comets, Oumuamua has neither bright hair nor a shiny dust tail. The curious visitor also stood out for its brilliance and wide variation in brightness. It looked like a metallic object reflecting light. Even stranger, after orbiting the Sun, it accelerated and deviated from its planned trajectory. The most likely explanation is that hydrogen trapped inside the object acted as a propellant. This would have been released by the Sun's heat. For the time being, it's being described as a comet. The absence of a tail is due to its small size. Observations planned for 2025 on small comets should enable us to find out more. We will have traveled not only within our solar system, but also beyond it with exoplanets. We've come across objects that stay in their orbits and others that hurtle through space. Some very large, some very small. Some very dense, others very bright. The search for new celestial bodies is endless. Enough to keep generations of astronomers and space enthusiasts dreaming. Nebulae play a vital role in the evolution of galaxies. By understanding how nebulae form and evolve, we can better understand the overall evolution of galaxies. Nebulae contain chemical elements that are essential building blocks for planets, stars, and life itself. They provide crucial information about the chemistry of the universe. By collecting data on nebulae and the regions in which new stars are formed, scientists are gathering elements for reconstructing the environment that existed in the early universe. The more distant the nebulae studied, the more the elements gathered helped to understand the first stages of cosmic evolution. Exceptional and unique astrophysical phenomena can occur in some of these nebulae. Observing them helps enrich our understanding of the universe. There are several types of nebula. The most common are emission nebulae, reflection nebulae, and obscure nebulae. Emission nebulae are bright. This is because their atoms are excited by ultraviolet radiation emitted by nearby young stars. The atoms, in turn, become a source of radiation. Reflection nebulae, on the other hand, emit no radiation themselves. They reflect the luminosity of the nearest stars, even reproducing their color. Dark nebulae, on the other hand, are dense concentrations of light-absorbing dust. They're only visible when there's a light source behind them, from which they can be detached. They're easy to observe and frequently even visible to the naked eye. But how were nebulae discovered, and how do they form? Nebulae are made up of gas and dust. The gas is partly of primordial origin. It formed early in the history of the universe, when hydrogen and helium, the building blocks of the first stars, appeared. The heavier elements are more recent. They are formed inside stars at the end of their existence, then released into the interstellar medium. The dust that makes up nebulae is a mixture of carbon at various levels of aggregation and silicates, along with trace amounts of other organic matter. The gas is essentially hydrogen. Nebulae are regions where the interstellar medium has become denser due to gravity. This has led to the formation of clouds that attract the surrounding matter once their mass and dimension have reached a sufficient size. These clouds can become visible when newly formed stars within them excite the atoms, making them luminous. Until 1780, the focus of astronomers' attention was on the stars. Scientists' attention slowly shifted in the direction of nebulae when in 1781, astronomer William Herschel discovered Uranus. King George III of England awarded him a royal pension, enabling him to invest in the construction of a new, more powerful telescope with which he could now study double stars. In all, the astronomer built over 400 telescopes. One of these remained the world's largest telescope for almost 50 years. This gigantic device could be operated by hand. With it, Herschel described and cataloged deep sky objects. In 1786, he published the catalog of 1,000 new nebulae and star clusters. He already distinguished between nebulae and star clusters. Over a period of 20 years, he listed more than 2,500 of them, and in 1811 completed his catalog with a list of 52 extremely diffuse nebulosities, which turned out to be integrated flow nebulae. In all, William Herschel published 4 catalogs describing over 5,000 deep sky objects. Other astronomers, such as John Dreyer, followed in his footsteps. In 1888, Dreyer published an NGC catalog describing over 7,800 celestial objects. Today, this catalog includes over 14,600 objects. The concept of the nebula, however, belongs to William Herschel. It was Herschel himself who identified the different types of nebula. The first planetary nebula discovered was the La Haltère Nebula, also known as the Dumbbell Nebula and referenced M27. Charles Messier recorded it in his catalog of diffuse objects, but the term planetary was proposed by William Herschel in 1785. In 1927, American astronomer Edward Emerson Bernard listed 349 obscure nebulae. Among the best known are the Horsehead Nebula, reference B33, and the Snakehead Nebula, reference B72. By this time, a number of nebulae had come to light, and scientists realized that this was an obscure world whose influence they were still unaware of. Everything was yet to be discovered. Edwin Hubble's work in 1924 made it possible to distinguish nebulae from galaxies. Although both contain gas and dust on a very different scale and in very different concentrations, their shape, dynamics, and size are very different. Nevertheless, in a small observation instrument, their appearance is more or less the same. Nebulae are warmly colored when photographed. They appear as a luminous region, rich in ionized gas ejected from stars or unused during their formation. The gas and dust present in the interstellar medium can materialize when excited by stellar radiation or backlit. This is how nebulae are classified. Emitting nebulae are gaseous formations that produce their own luminescence. They absorb light from a nearby hot star and emit it at lower energies in a variety of colors. They are said to be bright, as opposed to reflective nebulae, which simply reflect the light of nearby stars. Also known as IC 2177, the Seagull Nebula is a huge emission nebula. Seen from Earth, it is as large as 4 times the diameter of the full moon. The reddish glow of atomic hydrogen dominates, dotted with luminous young stars that stretch the length of the nebula. The name Seagull Nebula comes from its strong resemblance to the silhouette of a bird. This cosmic cloud is an ideal place for the formation of new stars. The Seagull Nebula is located 3,800 light-years from Earth and has a diameter of around 100 light-years. It contains several open clusters, including NGC 2343, NGC 2335, Calinder 465, and Calinder 466. This nebula is difficult to observe even under ideal viewing conditions, as its apparent magnitude is +10. The large number of stars in the nebula makes it impossible to see. The wings are almost impossible to see, unlike the head, referenced NGC 2327, which contains fewer stars. This is a region of compact emission in which a massive star is enclosed. There are several categories of emission nebulae. HII regions. These are regions of intense activity in which stars form. The Orion constellation is home to one of the most famous examples, the Orion Nebula, or M42. Its proximity to the Earth makes it one of the best known and most studied nebulae by scientists. Within the Orion Nebula, numerous stars and even planetary disks form. The nebula glows with fluorescence. Excited by the ultraviolet radiation of bright stars, gas atoms emit light. The color emitted depends on the type of atoms. Hydrogen, which is clearly in the majority in nebulae, emits predominantly red light, as does sulfur. Oxygen, on the other hand, emits green. Although our eyes are particularly poor at distinguishing colors at night, the Great Orion Nebula is an exception to this rule. Its contrasts allow observers to easily distinguish the nebula's colors. At first glance through binoculars, the Orion Nebula appears as a small cloud among the stars of Orion's sword. When viewed through a 60 to 80 millimeter telescope, its central region reveals a greenish hue. The jade hue intensifies when viewed through a more powerful telescope. As for the red, it remains indistinguishable, as our eyes are blind to this color at night. The accumulation of gas over tens of thousands of billions of kilometers gives the Orion Nebula a dense appearance, but this is only an illusion. The Orion Nebula has been known since ancient times. Astronomers have been observing it through telescopes for almost 4 centuries. As if petrified since the dawn of time, nothing in this immense interstellar cloud has ever moved. But it's only the nebula's enormous distance, almost 1,500 light-years, that makes us from Earth insensitive to its violent disturbances. This nebula is one of the largest in our Milky Way. It extends over a diameter of 24 light-years. Its mass is 2,000 times greater than that of our Sun. And yet, for all its immensity, it remains almost empty. Barely a few hundred atoms are present per cubic centimeter. The Orion Nebula is illuminated by 4 supergiant stars, forming an asterism that identifies the Orion trapezoid. Each of these stars shines 100,000 times brighter than the Sun. Their powerful ultraviolet radiation heats the gas, making it luminescent. As a result, the hydrogen clouds take on a flamingo pink hue, while the oxygen veils emit green radiation. These 4 supergiant stars don't just make light, they provoke a powerful stellar wind, blowing at over 100,000 kilometers per hour, or 62,000 miles per hour. Space is violently swept away, carrying clouds like storm clouds. Compressed gas becomes denser, and gravitation kicks in. Small globules of gas and dust form. They measure a few tens of billions of kilometers and resemble eggs that flatten on themselves under their own weight. As they collapse, the gas and dust that make them up are set into rotation. At the heart of these stars, a star is born. Having attracted matter to itself, it slowly pulls it out, blowing it around and beginning to shine. The 4 stars of Orion's trapezoid were born in this way around 200,000 years ago. By blowing the gas that gave them birth around them, they seed space and trigger the birth of new stars. The phenomenon of emission makes it possible to study nebulae using selective filters that exclude certain lines from the spectrum. Planetary nebulae are brightly colored and highly structured. They are associated with the death of low-mass stars like the Sun. Planetary nebulae are produced by the slow expulsion of gas from the surface layers of a star's atmosphere at the end of its life. All stars of mass equal to or less than the Sun end their lives by scattering the upper layers of their atmosphere into the surrounding medium. the material takes on a relatively regular disk shape, reminiscent of a planet. In fact, at the time of William Herschel's first observations, he observed the small star that remained visible at the center of the nebula, surrounded by a pale disk that gave the false impression that a planet was being born. Stars of greater mass also produce injections when they die, but these are much more brutal. The result is a supernova, or SNR for short. Although planetary nebulae and SNRs can sometimes be confused, there are many differences between them. Many planetary nebulae are easily accessible to professional and amateur astronomers from Earth. These include the Lyra Nebula M57, the Dumbbell Nebula M27, the Rosette Nebula NGC 2237-9, the Owl Nebula M97, and the Helix Nebula NGC 7293. The discovery of this type of nebula is well within the reach of amateur astronomers. 139 candidate planetary nebulae have been proposed, and some 20 have been confirmed. The Lyra Nebula is the most representative of all planetary nebulae. This star appears as a magnificent corona, surrounding the star as it dies out. The star's core is completely exposed, still glowing and illuminating the gas around it. The white dwarf at the center of the Lyra Nebula reaches 100,000 degrees Celsius, or 180,000 degrees Fahrenheit. By comparison, the Sun reaches 5,500 degrees Celsius. It has much more extensive extensions than the main ring, certainly the result of material ejected by the star before the nebula itself was formed. Planetary nebulae provide information not only on the star's constitution, but also on the date on which it expelled matter, by calculating the expansion velocity of the gases. The impressive dynamism of planetary nebulae is reflected in some cases by gas moving at speeds of up to 5,000 kilometers per second, or 3,100 miles per second. This creates exceptional shock waves and turbulence zones. Once the star has ejected up to 35% of its envelope, it ends its life as a dwarf star. One of the closest planetary nebulae to Earth is the Dumbbell M27 Nebula. It lies at a distance of around 650 light-years and exploded around 12,700 years ago. The Dumbbell Nebula was the first planetary nebula to be discovered. It is characterized by an original shape with two luminous lobes, giving it the appearance of a bell clapper, dumbbell, or apple core. This structure is known as bipolar and is found in other planetary nebulae, but never so pronounced. This characteristically asymmetrical shape is thought to have developed shortly before the star's death, as the dying star blew its atmosphere in two different directions. M27 is one of the largest planetary nebulae in the sky. Thanks to its age, it has expanded considerably. Although invisible to the naked eye, the Dumbbell Nebula is easily identifiable through binoculars. You can make out its dumbbell shape. Most planetary nebulae contain only a single star, but a few contain a binary system. Typically, this system consists of a very hot blue O-class star and a cooler A-class companion. The pair is rarely visible, as they are tightly packed together. The blue star emits mainly in the UV spectrum, while its companion emits in the visible spectrum, making it impossible to observe the star at the source of the excitation. Examples of double-core planetary nebulae include NGC 3132, NGC 1514, and the Boomerang Nebula. The latter is currently the coldest place in the universe. Located 5,000 light-years from Earth in the constellation Centauri, its temperature is minus 272 degrees Celsius or minus 169 degrees Fahrenheit. It's colder than the cosmic microwave background and the only known natural object of its kind. But why has it reached such a cold temperature? At the heart of this nebula lies a star 4 times more massive than the Sun. But this star hides a secret. 3,500 years ago, it was the result of the fusion of 2 other stars. Without this fusion, the gas in the nebula would not reach such extreme temperatures today. In fact, the Boomerang Nebula's low temperature is due to its gas being expelled in very large quantities and at extremely high velocities. A team of astronomers has taken into account the envelope's expansion velocity, which is 150 kilometers per second, or 90 miles per second, 10 times greater than that usually expelled by a red giant. Scientists have shown that the only way to produce such a quantity of gas at such a speed would be to use energy from the interaction of 2 stars. A few thousand years ago, the red giant would have trapped a companion star in its envelope. The interaction of the 2 stars produced an impetuous ejection of matter. The nebula is now shaped like an hourglass, 20,000 astronomical units long. This peculiar shape is due to the jet produced by the central star, which pushes back cold gas locally. Another planetary nebula containing a binary system that commands admiration for its marvelous shape is the PN M2-9 Nebula, nicknamed the Butterfly Nebula or Twin Jet Nebula. This nebula is characterized by a surprising complexity that takes the form of 2 wings around a heart. The core is made up of 2 old stars that change appearance and state to become white dwarfs. Their total disappearance will only occur in a few billion years' time. In the meantime, they never cease to amaze with their sumptuous designs. Located some 4,000 light-years from Earth in the constellation Ophiuchus, the Butterfly Nebula owes its wings to 2 stars of equivalent mass that emit 2 great expanses of gas. The smaller of the 2 has a mass between 0.6 and 1 times the mass of the Sun, and is already a white dwarf. Its companion is estimated to have between 1 and 1.4 times the mass of the Sun. It has already released its outer layers. The expansion of the gas that forms these fascinating butterfly wings is thought to have begun around 1,200 years ago. The nebula contains, inside a shell of gas, 2 jets expelling matter at a speed of over 1 million kilometers per hour, or more than 620,000 miles per hour. Scientists also recently discovered that a disk of gas 15 times larger than Pluto's orbit surrounds the 2 stars. It turns out that the star, which has already taken on the form of a white dwarf, is in the process of stripping its fading companion. NGC 1514, also known as the Crystal Ball Nebula, is a planetary nebula located in the constellation Taurus, some 800 light-years from Earth. It was discovered by astronomer William Herschel in 1790. The nebula is characterized by its ring-pair shape. This double structure is explained by the presence of a binary system of aging stars at the nebula's center. In concrete terms, the nebula appears as a double shell, with a very bright envelope in the center and a thinner one on the outside. At the center of the nebula, the two stars revolve around a common center of gravity, with a period of 4 to 9 days. NGC 6302, the Insect Nebula, or M2-9, also known as the Butterfly Nebula, or Caldwell 69, is a bipolar planetary nebula with one of the most complex structures ever observed in a planetary nebula. It lies around 3,500 light-years from Earth, in the constellation Scorpius. As they age, stars can take on structures sometimes similar to flowers or insects. This is the case of the Insect Nebula, which has a wingspan of 3 light-years. Its central star, at the end of its life, has a temperature of over 200,000 degrees Celsius, or 360,000 degrees Fahrenheit, suggesting that it was originally very large. The white dwarf's mass is around 0.64 times that of the Sun. It is surrounded by a dense disk of gas and dust. It is the same disk that gives the nebula its hourglass-like bipolar structure. The Insect Nebula consists of 2 primary lobes. A wide dark band runs through the middle of the nebula, plunging the central star into darkness at every length. This band has an exceptional chemical composition. Scientists have detected ice crystals, quartz, and numerous silicates. The characteristic feature of the nebula is that it is composed of both oxygen-rich and carbon-rich minerals. In most cases, these minerals do not coexist. Stars are basically rich in one or the other, and the transition from the first state to the second occurs as the star ages. This suggests that the hydrocarbon molecules in the Insect Nebula were formed in an oxygen-rich environment. The Insect Nebula is prone to strange projections of matter, in the part representing its wings. These jets are projected at more than 1,000 kilometers per second, and asymmetrically. They intersect and form disordered structures. Some researchers have speculated that these ejections could be due to the central white dwarf merging with another star. However, in the absence of visibility at the center of the nebula, this hypothesis remains unconfirmed. A supernova defines the set of phenomena resulting from the gigantic explosion of a star at the end of its life. For a time, the supernova can shine brighter than an entire galaxy of billions of stars. From Earth, a supernova looks like a new star, when in fact it's the sign of a star's demise. A core collapse supernova is characterized by a massive star that stops producing energy from nuclear fusion in its core. It then collapses under its own gravity. A thermonuclear supernova occurs when a white dwarf has stored enough material for a companion star to reach a critical mass, triggering a thermonuclear explosion. the exploding star is totally destroyed, while the companion star may in some cases survive. When a supernova explodes, an enormous quantity of ejecta is expelled, of the order of several solar masses, at speeds of up to 10,000 kilometers per second or 18,000 miles per second. The shock front resulting from the rapid expansion of this material forms the visible part of the afterglow. Supernova remnants are defined by the structure produced by the expanding supernova ejecta. Many slags retain a regular shape for a long time, depending on whether they have an internal energy source, such as a central pulsar, or not. To better understand supernova afterglows, let's look up to the sky. Against the stellar backdrop of the Milky Way, a pretty gray blob appears through a small 60mm telescope. With a 100 to 200mm telescope, we can see a well-defined S-shape. With an even more powerful instrument, it's possible to make out gaseous filaments floating in the sky. This is one of the best-known and most studied examples of supernova afterglow. Messier 1, or the Crab Nebula, some 6,300 light-years from Earth. This nebula reminds us that a supernova exploded at this very spot in the year 1054 in the constellation Taurus. In July 1054, Chinese astronomers spotted a new star in the Taurus constellation. They called it a guest star. However, its brilliance intensified to the point where it surpassed that of Venus. It remained visible for 3 weeks in daylight, with a magnitude of between -3 and -5, and appeared for 2 years at night. Around 7 centuries later, in 1758, the astronomer and famous comet hunter Charles Messier, while searching the sky for Halley's Comet, spotted a small nebula in the constellation Taurus. He gave it the number 1. It wasn't until 1928 that Edwin Hubble made the connection between the famous guest star of 1054 and this Messier 1 nebula, nicknamed the Crab Nebula, in reference to the expanding gas released by the supernova. It continues to grow at a speed of 1,500 kilometers per second, or 930 miles per second. The debris forming the nebula is made up of ionized helium and hydrogen, and has a temperature in excess of 10,000 degrees Celsius, or 18,000 degrees Fahrenheit. It will dilute in the cosmos over the coming millennia. The Crab Nebula has a pulsar at its center, called the Crab Pulsar. It rotates about 30 times per second. This pulsar emits 200,000 times more energy than the Sun, making it the most energetic pulsar known. Its diameter is estimated at 30 kilometers or 18 miles. It is responsible for the central illumination of the nebula. The nebula lies in the immediate vicinity of the ecliptic plane, making it an interesting source of radiation for studying other celestial bodies. By observing its radio waves or X-rays, it is possible to measure and study other nearby objects. Wolf-Rayet bubbles are located around Wolf-Rayet stars. These are defined as hot stars with masses tens of times that of the Sun. They are characterized by the fact that during a relatively brief phase following the main sequence, they eject the matter around their core in the form of very violent stellar winds. The core is then exposed and explodes into a supernova. Wolf-Rayet bubbles are particularly active, emitting huge quantities of gas as a result of thermonuclear reactions in their cores. The two most famous of these are the Crescent Nebula, NGC 6888, and Thor's Helmet Nebula, NGC 2359. The Crescent Nebula NGC 6888 is located in the constellation Cygnus, some 5,000 light-years from Earth. This region is particularly renowned for its wealth of nebulae. The Wolf-Rayet star, WR136 at its center, generates violent stellar winds that push the ejected matter outwards. This cosmic bubble, some 25 light-years across, paints a splendid picture of the nebula through telescopes. The structures of the Crescent Nebula are the result of the interaction between the strong wind and matter ejected in the past. This star is nearing the end of its life and is expected to explode into a supernova. Thor's Helmet Nebula, NGC 2359, is a nebula in the Big Dog constellation, around 15,000 light-years from the solar system. It has the peculiar shape of a bubble, blown by a massive star with complex filaments. The Wolf-Rayet WR7 star at its center is extremely hot. The nebula's emerald green color is the result of strong emissions from the oxygen atoms in the cloud. Reflection nebulae are dust clouds that reflect the light of one or more nearby stars. These stars are bright enough to make the dust visible, but not hot enough to ionize the gas. Reflection nebulae are hotspots for star formation. The best known and most studied reflection nebula is that surrounding the Pleiades cluster, also known as M45. The Pleiades cluster is a celestial figure known since at least Neolithic times. Its appearance in the morning sky heralded harvest time. Although only a small number of stars are visible to the naked eye, this cluster is extremely rich, containing several thousand in all. The Pleiades cluster is around 100 million years old, and astronomers estimate that it will disperse into the Milky Way within 200 to 300 million years due to its low compactness. The blue nebula that surrounds this cluster is the beauty of the photographs. Emission and reflection nebulae form the group of diffuse nebulae, distinguished by their luminous emission. On the other hand, there are dark nebulae. The latter are regions in which dust from the interstellar medium concentrates in immense clouds that appear in starless regions. They are visible when they obscure part of an emitting or reflecting nebula. Ever since human beings decided to take an interest in the sky, they have been able to observe dark spots in regions of high stellar density that appear to be devoid of stars. They have put forward two hypotheses. Either these dark zones correspond to the distribution of stars, or they represent dark masses appearing as opaque screens. The first view was quickly discarded after the study of the celestial distribution of objects, since it is unlikely that immense starless pipes exist over lengths of several thousand parsecs. So it's not surprising that there are superpositions of dark clouds. Many known nebulous objects show absorption marks in the form of small black globules or thin opaque filaments. The density of these dark nebulae prevents the passage of light. The Milky Way has been studied from top to bottom since the invention of the telescope. This has revealed some 200 regions in the sky that appear to be devoid of stars. In reality, they contain dark nebulae with stars unable to illuminate them. The material is thus condensed and opaque to radiation, positioning itself in front of brightly lit regions of the Milky Way. To study these dark nebulae, you need to get as far away as possible from pollution and artificial light. Within them, a tiny fraction of the incident light crosses the matter barrier formed by the clouds. This makes them veritable radiation traps. Astronomers have therefore used derivative techniques such as infrared or radio to observe them. These dark clouds are neither too thick nor too dense. Infrared techniques are able to penetrate them and observe the objects behind them. Dark nebulae are among the coldest and largest bodies in our galaxy. They are made up of molecular hydrogen and a variety of dusts whose grains, a mixture of silicate, graphite, ice, and various ferrous metals, provide sufficient opacity. Nebulae can also be distinguished by their thickness. The largest of them can contain up to 100 solar masses of dust. One of the best examples of this type of nebula is the charcoal bag. This large dark nebula occupies an area on the celestial vault equivalent to some 30 full moons. It can be found 600 light-years away, in the Southern Cross constellation, in front of luminous sections of the Milky Way. Spanish explorer Vicente Yanez Pinzon first spotted this dark spot in 1499. He was the navigator and commander of La Niña, one of the 3 ships that first landed in America under the command of Christopher Columbus. The nebula was nicknamed Magellan's Dark Cloud because of its opacity and in comparison with the 2 bright Magellanic Clouds. Seen with the naked eye from the southern hemisphere, the charcoal bag can be spotted lurking against the stars of the Southern Cross. With binoculars, it's easy to spot, thanks to its irregular contours. This coal-black nebula is so vast that it doesn't fit entirely within the field of a telescope. Nevertheless, a telescope can observe one of the most beautiful star clusters nearby. It's called the Jewel Box because its stars are compared to sparkling gems. The obscure Horsehead Nebula, also known as Barnard 33, is located in one of the youngest regions of the sky, the constellation Orion. At the end of December, during the winter solstice, the night-darkened hemisphere of Earth comes face to face with a stellar region of our galaxy. Stars, each more beautiful and brilliant than the last, light up the Milky Way like rubies, diamonds, and sapphires. The brightest and closest is Sirius. 100 times further on is the supergiant Rigel, which, along with Betelgeuse, Bellatrix, and Siph, forms the constellation Orion. Not far from the center of this constellation, patience and perseverance are required to find the Horsehead Nebula just below the star Alnitak. Here, immense clouds of gas give birth to new stars. This nebula is made up of interstellar gas and dust that light is unable to penetrate. It is therefore invisible to the naked eye. Its horsehead shape is caused by the presence of a dense cloud of gas and dust. At the base of the head are young stars in the process of forming. The Horsehead Nebula is about 7 light-years long and lies almost 1,500 light-years from us. It does not radiate and is very dense and cold. Some nebulae are said to be chaotic because they are unique in that they are both emitting and dark at the same time. The gases they contain take on highly varied appearances, and the environment is disturbed. Examples include the Sorcerer's Nebula, NGC 7380, the IC 1318 Nebula, and the North American Nebula, NGC 7000. Close to Deneb, the brightest star in the Cygnus, lies the North American Nebula, NGC 7000, in the Cygnus constellation. It is closely accompanied by a neighboring nebula nicknamed the Pelican, IC 5070. The mass of gas contained in these two nebulae is estimated at 5,000 solar masses. Between them, they form the visible part of an immense hydrogen cloud. Scientists thought that the nearby supergiant star Deneb would provide them with the energy they needed to fluoresce. As it turns out, this star isn't hot enough at 8,230 degrees Celsius or 14,900 degrees Fahrenheit, and the nebula needs to be heated by a star with a temperature above 30,000 degrees Celsius or 54,000 degrees Fahrenheit. What's more, Deneb is too far from the nebula complex. The ionizing star is actually at the rear of the nebula. Its surface temperature exceeds 40,000 degrees Celsius, or 72,000 degrees Fahrenheit, and it belongs to a binary system. The light emitted cuts the contours of the clouds in such a way as to remind us from Earth of the North American continent. The Swan Wall is a region reminiscent of Mexico and Central America. It is in this region of the nebula that we find the highest rate of star formation. The North American Nebula is only visible in excellent skies. Although it emits a not inconsiderable light of magnitude 5, it extends over such a vast area that it is difficult to see. It covers an area more than 10 times that of the full moon. The Sorcerer's Nebula, NGC 7380, is so named because seen in profile, its contours evoke the figure of a sorcerer. From above, you can make out his hat, eye, nose, mouth, and long beard. This nebula is located in the Cepheus constellation, some 8,000 light-years from Earth. It is surrounded by an open cluster. The nebula and cluster form a favorable environment for the birth of new stars and the creation of new planets. The Sorcerer's Nebula is not easily identifiable on the celestial vault. It requires very good observation conditions, as well as the use of precise instruments such as a telescope with a diameter of at least 200 millimeters. The IC 1318 Nebula, also known as the Butterfly Nebula, is located in the constellation Cygnus. This brightly emitting nebula has a dark nebula at its center. Its circumflex shape is clearly visible in the photographs. Since 1976, another category of nebulae has also been described: integrated flow nebulae, or IFNs. An integrated flux nebula is illuminated solely by the luminous halo emitted by the entire galaxy it inhabits, the so-called integrated flux. This type of nebula has been observed in the Milky Way. These clouds are made up of dust present in the interstellar medium at all galactic latitudes. Their colors stand out in very long exposure photographs, but do not show up in binoculars or telescopes unless the optics are very bright and the observation site is shielded from artificial light. The best-known nebulae owe their success to their proximity to the Earth. Astronomers, whether professional or amateur, choose objects that are easily accessible and within reach of their instruments. Within the Milky Way, most of the nebulae observed are located close to the Sun, within a radius of 5,000 light-years between the Orion Arm and the Carina-Sagittaria Arm. Nebulae in the direction of the galactic bulge are difficult to spot, as the stars and dust clouds there are far too dense. As for the rest of the universe beyond the Milky Way, it also contains some astonishing nebulae. Outside the Milky Way, it's difficult to identify specific individual nebulae with the same notoriety as those in our own galaxy. Nevertheless, there are some complex nebulous regions in other galaxies that are well known to astronomers and astronomy enthusiasts. We won't necessarily find individual planetary nebulae like those in the Milky Way. The galaxy itself may contain various nebulous regions due to star formation processes. Specific observations and discoveries may vary over time due to advances in astronomy and imaging. The brightness of the Magellanic Clouds is comparable to that of the Milky Way. In the southern hemisphere, and in the absence of light pollution, they both appear distinctly without the need for observational instruments. If you use binoculars, their characteristic shapes are clearly visible. The Large Cloud Galaxy measures the equivalent of 20 full moons lined up end to end. The Small Cloud Galaxy, on the other hand, is 3 times smaller. The Magellanic Clouds are the Milky Way's 2 largest satellite galaxies. The Large Cloud is 160,000 light-years from the Sun, while the Small Cloud is 200,000 light-years away. Although not the closest to the Milky Way, the galaxies of the Magellanic Clouds are still the easiest to observe. They are certainly ancient barred spiral galaxies, distorted by the gravitational pull of the Milky Way. The Small Cloud Galaxy contains around 3 billion stars, while the Large Cloud Galaxy has 10 times that number. Within the latter, we find one of the largest nebulae known in the universe, the Tarantula Nebula. A vast patch of interstellar fog is visible within the Large Magellanic Cloud. This is the Tarantula Nebula, also known as NGC 2070. Seeing the images of this nebula, it's easy to understand why this sprawling mixture of gas and stars is likened to a spider. Located 160,000 light-years from Earth, the Tarantula Nebula seems rather modest. But it's its remoteness that's misleading. If the Tarantula were as close to us as the Orion Nebula, it would cover a quarter of our sky and be visible even in broad daylight. Within this gigantic gaseous labyrinth lie some of the most massive stars known to man. Like a colossal matrix of stars, the Tarantula Nebula exceeds 1,800 light-years in diameter. It is the largest nebula known to date. Its star formation rate is higher than in any other region of the Milky Way. Shielded from light pollution, the nebula appears as a small bright spot in the immediate vicinity of the Large Magellanic Cloud. Its magnitude of around 5 makes it easily visible to the naked eye. At the heart of the nebula is a dense cluster of hot stars that produce the ultraviolet radiation that ionizes the surrounding gas. This is what makes the nebula visible. The cluster of stars is called R136a. It includes the most massive star ever observed, R136a1 beats the Sun in every respect. It is comparatively 30 times wider, 8 million times brighter, and has a surface temperature 10 times higher than the Sun. The nebula contains a large number of star-forming stars. It turns out that star formation in this nebula is quite different from that in other galaxies such as the Milky Way. Scientists have discovered that the star-forming regions within the Tarantula Nebula are producing stars at a far greater rate than in the Milky Way. These discoveries provide new insights into the history of stellar creation. The chemical composition of the tarantula is similar to certain star-forming regions that existed when the universe was very young, only a few billion years ago. This subject of study continues to interest scientists as they seek to learn even more about this nebula. The Tarantula Nebula emits a reddish light due to the excitation of hydrogen. The powerful light rays from giant stars burn the gas so intensely that they eventually explode into supernovas. In 1987, at the edge of the Tarantula Nebula, a supernova, visible to the naked eye, lit up the sky, leaving behind an afterglow that is now well known and still observed. In 1987, the Large Magellanic Cloud Galaxy was the site of the brightest supernova recorded in the last 400 years. A star with a mass equivalent to 20 solar masses exploded. SN 1987A was the first supernova explosion of the 20th century to be observed with the naked eye, far from light pollution. It was then observed continuously in all usable ranges of electromagnetic radiation. This supernova is one of astronomy's most important objects, as it is the first time that the progenitor star is known before the explosion. The phenomenon occurred on the night of February 23, 1987, some 165,000 light-years from Earth. It was the closest supernova observed outside our galaxy. Around 3 months later, in May, its brightness peaked at an apparent magnitude of around +3, before declining over the following months. The progenitor star is a blue supergiant with an initial mass of around 20 solar masses. It is named Sandalik -69 degrees 202A and formed 10 million years ago. Scientists were astonished that it was a blue supergiant and not a red one, since at the time it was considered that only red supergiants evolved into supernovas. Thanks to the Hubble telescope, scientists were able to analyze Sandalik -69 degrees 202A and deduced that it must have evolved from a red to a blue supergiant before exploding. In fact, 3 rings of gas orbit SN 1987A, dating back 20,000 years before the explosion. The star must have lost mass before its explosion, which explains its change in type. Its rings have adopted a distinctive morphology. The 2 outer rings are hourglass-shaped, while a smaller inner ring forms the neck. This characteristic may be linked to the violent solar winds that sculpted this extraordinary shape. The 2 outer rings may also have been illuminated by the gas ejected in the supernova. The supernova afterglow has always been visible. It is the object of intense observation, since it is the youngest known afterglow. All these years of observation of SN 1987A are of immense value. The data enable scientists to better understand the final stages in the evolution of stars. Supernovas are of considerable importance in the history of the universe. They expel the elements that form at the heart of stars, such as iron, oxygen, nitrogen, and carbon. Depending on the strength of the explosion, they can also feed energy into gas clouds, helping to give birth to new stars. By studying supernova 1987A from the moment of its explosion, astronomers have gained a better understanding of the very first stages in the dispersal of the afterglow, and the effects this will have on the supernova's environment. The Lobster Nebula is located in the smallest of the dwarf galaxies in the Magellanic Cloud. It spans about 400 light-years and is about 5,500 light-years from Earth. A blue glow from the emission of ionized hydrogen gas surrounds this star-forming region. The surrounding nebula appears as a mixture of gas, dark dust, stars in formation, and newborn stars. This complex architecture is the result of interactions between interstellar winds, magnetic fields, gravitational interactions, and radiation pressure. The Lobster Nebula harbors an open cluster near its center, containing stars of exceptional brilliance and mass. This is the Pismis 24 open cluster. This cluster contains many massive stars. Among them, Pismis 24-1 is 776,000 times brighter than the Sun. Its mass approaches 300 solar masses. It is in fact a system of at least 3 stars. Pismis 24 is one of the most active sites of massive star formation. NGC 346 is an emission nebula associated with an open cluster. It lies within the small Magellanic Cloud in the constellation of the Toucan. It was discovered by astronomer James Dunlop in 1826. NGC 346 lies some 200,000 light-years away. This intense star-forming region has a diameter of around 200 light-years. NGC 346 is a true wonder of the southern sky. By studying it, astronomers have been able to discover a population of embryonic stars in formation. These are arranged along the dark bands of visible dust. The very young stars continue to collapse into their initial clouds, emitting a light that is reddened by the dust between them and the Earth. This stellar nursery closely resembles those that remain in the primordial universe. Scientists estimate that 2% of the 200 billion galaxies in the universe interact with a nearby galaxy. Such is the case with the famous Hound Dog Galaxy, also known as the Whirlpool Galaxy and referenced M51. It lies at an abysmal distance of 23 million light-years from us. Messier 51 is the common name for the 2 stars because Charles Messier did not split them at the time. In fact, they are a pair of interacting galaxies. The small galaxy NGC 5195 lies a few tens of thousands of light-years behind its big sister, NGC 5194. The former is so distorted by the interaction, which has been going on for almost 1 billion years, that astronomers can't classify it. The interaction of these 2 galaxies is causing outbreaks of new stars. In the larger of the 2 galaxies, no fewer than 100 ionized nebulae have been detected. No one knows how the encounter will end. Will the 2 stars separate and drift apart, or merge into a single galaxy? Our planet's nocturnal orientation, away from the galactic disk that illuminates summer and winter nights, is directed in spring towards the constellations with the fewest stars and interstellar gas, such as Leo, Virgo, the Big Dipper, and the Hounds. It's in these endless transparent regions of the sky, seemingly devoid of stars, that astronomers enjoy observing the most distant objects under the best conditions. Among them, the Hound Dog Spiral is one of the brightest and most beautiful galaxies known. Despite its impressive diameter of over 60,000 light-years, it is invisible to the naked eye. It is populated by over 200 billion stars. The pair of galaxies is bound together by the force of gravity. The spiral structure of NGC 5194 is strongly disrupted by the passage of its smaller companion. The galaxy's sumptuous brilliance is due to the gravitational tidal forces generated by the small galaxy. In the same way that the Moon influences the oceanic masses of the Earth, NGC 5195 acts on the gas masses of NGC 5194. This interaction suppresses interstellar gas, which condenses into new stars. As a result, the spiral disk of the Hound Dog galaxy is rich in nebulae. In close-up photographs of the galaxy's disk, we can see its youth and vitality in the brilliant nebulae illuminated by the thousands of supergiant stars they give birth to a few 100 million years ago. Only stars 1,000 to 10,000 times brighter than the Sun are visible. The billions of others are too dim to be seen individually. The barred spiral galaxy NGC 1313 is located in the constellation Reticule. It is one of the smallest and least luminous constellations in the southern hemisphere, and contains one of the most remarkable celestial objects. This galaxy lies some 13.5 million light-years from Earth. This gravitationally isolated galaxy shares some characteristics with the Magellanic Clouds. Its spiral arms are weakly coiled and attached to the end of its bar. They are uneven, revealing globules of gas. What's more, they don't rotate at the center of the bar, which is also a sign that the galaxy has undergone disturbances. Its morphology suggests that its past must have been highly turbulent. NGC 1313 is thought to have interacted with a smaller galaxy in the past. This highly active galaxy features a large number of nebulae surrounded by gas. The arms of the galaxy feature numerous star-forming sites and open clusters of young stars. The radiation from all these fledgling stars generates gas that creates beautiful patterns of light and dark nebulae. NGC 1313 is a star-forming galaxy, a feature that remains enigmatic as the galaxy remains relatively isolated. Indeed, in most galaxies of this type, the high rate of star formation is due to a meeting or even a merger of two galaxies. In the constellation Perseus, NGC 1275 is a lenticular galaxy, around 250 million light-years from Earth, with a diameter of over 250,000 light-years. This vast galaxy is characterized by highly complex dynamics that set it apart from other galaxies. Located at the heart of the Perseus galaxy cluster, it is bathed in hot, diffuse gas with an average temperature of several tens of millions of degrees. It is this gas that forms most of the luminous mass of galaxy clusters. The matter that forms the environment is highly complex. On the one hand, the hot gas causes cooling, and on the other, the supermassive black hole, with a mass equivalent to around 340 million solar masses, generates powerful, high-energy jets that prevent the gas from cooling completely. The result is a sumptuous network of filaments surrounding NGC 1275. This large nebula extends over 250 light-years, equivalent to 2.5 times the size of the Milky Way. The motion of the network of filaments is not uniform, but rather chaotic. This dynamic may be intimately linked to the heating and cooling of the gas that feeds the black hole at the heart of the galaxy. NGC 2403, also known as Caldwell 7, is a spiral galaxy in the constellation Giraffe, around 8.5 million light-years from the Milky Way. In the galaxy's eastern outer arm lies NGC 2404, an open cluster of stars. It is associated with an emission nebula. NGC 2403's spiral arms are illuminated by bright red nebulae, a few bluish open clusters, and dark veins of dust. At its heart, the nucleus is bright but relatively small. According to some scientists, this galaxy is gravitationally part of the Messier 81 group. Around 15 million light-years from Earth, Messier 83, a spiral galaxy, is majestically visible. Beside it is a small quasi-elliptical nebula, the dwarf galaxy NGC 5253. Although it may seem rather insignificant at first glance, it is a site of intense star formation. This compact blue dwarf galaxy is located in the constellation Centauri. It has a magnitude of 10.5. It is one of the closest blue compact dwarf galaxies to us. Vivid blue and violet colors are visible through observational instruments, due to its active star formation. NGC 5253 is home to very active star-forming regions, although it contains little dust, hydrogen, and helium, the basic elements for star formation. These molecular clouds strongly resemble the clouds that form the first stars in the early universe. This is why scientists like to study compact blue dwarf galaxies, to better understand the primordial process of star formation. NGC 5253 features a central starburst zone rich in hot young stars concentrated in a star cluster. Its morphology is not uniform due to the intense consumption of gas. At its heart is a gigantic supercluster of over 1 million stars, each 3 million years old. The total luminosity of this supercluster is equivalent to around 1 billion times that of the Sun. From Earth, it is completely invisible, as it is obscured by a giant dust cloud. The local group is a collection of 60 galaxies spanning 10 million light-years. Among them, the Milky Way and the Andromeda Galaxy are the main members. The third largest galaxy is the Triangulum, also known as M33. To spot the Triangulum Galaxy with the naked eye, you need a pure black sky and the eyes of an eagle. Nevertheless, it is easily visible through binoculars. Its oval disk is uniformly bright, although a slight excess of brightness towards the center betrays the presence of the bulge. Through a 300 to 400 millimeter telescope, we can easily observe its sumptuous spiral arms. The Triangulum Galaxy has particularly well-developed spiral arms, which appear spectacularly when viewed from the front. Yet it remains modest in comparison to the Milky Way and Andromeda galaxies, containing just 40 billion stars. Its very active arms are filled with regions of ionized gas, within which stars are born by the hundreds. The largest of these nebulae is NGC 604, the Triangulum Nebula. The Triangle Nebula, also known as NGC 604, spans 1,500 light-years and shines 6,000 times brighter than the Orion Nebula. Its immense tentacles of cold gas extend far beyond the visible disk. It was discovered by astronomer William Herschel on September 11, 1784. It lies nearly 3 million light-years from Earth. If it were at the same distance as the Orion Nebula, it would surpass the brilliance of Venus. It's an emission nebula with around 200 stars at its heart, with masses ranging from 15 to 60 solar masses. It is this same cluster of stars that irradiates the gas with energetic ultraviolet light, stripping electrons from atoms and producing the special glow of nebulae. A hot, sparse gas that emits X-rays fills the bubbles and cavities of the nebula. The tarantula, the crab, the lobster, the owl, the butterfly, and many others are silent witnesses to the grandeur and complexity of our universe. This journey through the nebulae helps us understand the significant importance of these stellar objects. Since mankind first discovered and studied nebulae, new data have been added to our understanding of star formation, galactic evolution, and cosmic chemistry. These vast clouds of gas and dust, which often take on the appearance of creatures and animals, can be found everywhere in the Milky Way and beyond. They are ideal places for the formation of new stars and planets, and shape the cosmic architecture. The study of nebulae continues to fuel our quest for understanding. The mysterious secrets of the early universe are gradually being revealed, reminding us of the complexity of the universe around us. To what extent do nebulae hold the answers to the fundamental enigmas of our universe? The exploration of nebulae is far from over, and they remain a dynamic area of research in astronomy. Despite the enormous progress scientists have made in understanding nebulae over the decades, there is still much to discover. Astronomers are trying to understand many mysteries, such as the precise details of star formation inside nebulae, the exact mechanisms of their evolution, or their role in galactic evolution. New technologies, more powerful telescopes, space missions, and advances in observation techniques continue to open up new perspectives. Many more revelations await us in these vast stellar clouds.